Welcome back, students. So we lastly have talked about one type of hybrid materials, that is what we refer to as composite materials as a type of hybrid materials and their utilization. So what we have learned by now is that what are the basic constituents of a composite and how we can predict the properties of a composite material. We have also seen that the resulting properties of the composite material are better than the properties of the individual constituents as such, and they are better placed on material property charts in terms of material indices. In the same context, talking about the hybrid materials itself, we now talk about another category of hybrid materials which we say is called as sandwich panels. Now, going forward, sandwich panels, when I say that a sandwich panel basically is a panel which has faces just shown here. The faces which are represented here as made of material A, and there is a core which we are saying is material B. So traditionally the faces are made of strong and stiff material, maybe a metal or a CFRP, and the core itself is made up of lightweight material. Maybe now there are various types of core materials which we'll try to refer to in our next discussions. Foams are most commonly used core materials for sandwich structures. Honeycombs are another ones here. There are some variations in terms of textile fabric which can also be used as a core material. So when I refer to the sandwich panel itself, it has normally two stiff and strong skins, what also called as faces, which are separated by a light core. Normally, a sandwich panel may be it may be undertaking bending loads, and it may be then understood as a sandwich beam also. That is what we'll try to analyze it as a sandwich beam itself. So what we see here is that because the skins or the faces are separated by a large distance c here, each skin or face have a face thickness of t, and d happens to be the total thickness of the sandwich itself. So the separation of the skins here, because they are separated by a distance c from the neutral axis, if you say it is subjected to bending, so this will itself increase the moment of inertia of the section, which will in turn give us a better bending performance. In analogous example of that, of a sandwich structure or a sandwich beam, happens to be just like an I-beam. So if you recall basic strength of materials, we have seen that you make an I-beam which has a thin web, and the flanges are there. The flanges are separated at a large distance from the neutral axis. So on the same lines, we can say that in a sandwich panel or in a sandwich structure, the face or the skin here is representing the flanges, and the core material is representing the web of the I section. But there is more to it in terms of a sandwich material. I section or a I beam, normally if it is made of a if it's made of a homogeneous material, which is a monolithic material, it will have the same density at the face and as well as at the core. Whereas because the sandwich structure is made up of a core material which is much lighter than the face material here, that is why the sandwich structure that you develop here, in addition to behaving like an I section, it will also give you weight saving, because the core material is traditionally a very lightweight material, and the overall mass of the sandwich structure is reduced to a great extent. And this is one of the basic reasons why sandwich panels are mostly used in aerospace applications. They have got wide application in terms of in aerospace industry. You can see that most of the floorings that you use for an aircraft, specifically a passenger aircraft, is made up of sandwich panels. Most of the doors, most of the partitions that you find in a commercial airliner, they are actually nothing but a sandwich panel there. So we will see that how we can analyze these sandwich materials to some extent. It's a very broad area itself, and calls for a full course even on analysis of sandwich structures, but we will try to discuss the basic requirements which are essential for us to make us understand that how sandwich materials behave differently or than the monolithic materials of which they are made up of, and what is the advantage that we gain out of this. Okay, so when I talk about the sandwich panels, the basic terms that we will be using here is a core material and a face material. The core thickness is referred to as C, the face thickness is referred to as T, and D happens to be the total thickness of the sandwich, which is nothing but C plus 2T. And if it is behaving as a beam, then L happens to be the span length of the beam and B happens to be the width of the beam. Normally, we have already said that the faces are made up of materials which are having high stiffness and strength. Traditionally, they are made up of metals or of composites as such. Cores, as we say, can be of various types, foams, honeycombs, etc. Foam cores are traditionally heavier than honeycombs here. When I talk about the mechanical behavior of the sandwich structure or a panel itself, it depends upon the properties of the face material, that what is the face material A, the properties of the core material, as well as the geometry. The term geometry here means that what is the relative thickness between what is the relative thickness in terms of C and T, whether C is too large, T is very small, or C is small, T is large. That is what we mean by the term geometry here. We will make it more clear, we will make it more understandable in terms of the same expression of the volume fraction which we use in the case of our composite material discussion. So here also in a sandwich panel also we will go by the same definition of the volume fraction, and we'll talk about the volume fraction of the face material. We'll see how do we calculate that. So what we are trying to say here is that how this sandwich behaves mechanically will depend upon the material of the face, the material of the core, and the geometry means what is the core thickness and the what we say as the face thickness, as well as the loading conditions, as well as whether it is supported as a simply supported beam or a cantilever beam or a different type of a beam. Normally, in the discussions on sandwich structures, minimization of the mass for a given strength or a stiffness happens to be the basic design objective here. So, going forward with our discussion on what are the various core materials here. So, we can classify the core materials into two basic categories. One of them is homogeneous cores and second one is non-homogeneous cores. Homogeneous cores are traditionally called as foam cores. We'll talk about these foam cores and then go to the non-homogeneous later on. So when I talk about the foam cores here, we can say that the foams that you use here as a core, the black portion here, can be open cell foam or a closed cell foam. So what is the meaning of the open cell foam or a closed cell foam is shown here. So we understand that how do you create a foam? You take a solid material, maybe a polymer, and blow a gas or a blowing agent or air through it, which creates pores inside it. So which will actually give rise to foamification, which reduces the relative density of the foam with respect to the density of the solid of which this foam is made of. So these areas, these volumes are referred to as cells. So this is a cell, this is another cell, this is another cell, this is another cell, and here also this is a cell. So there are two basic categorizations of foams to begin with: open cell foams and closed cell foams. Visually you can see that this is an open cell foam and this is a closed cell foam. In an open cell foam, the cells are not isolated from each other, they are open to each other here, whereas in a closed cell foam, the cells, this cell, the second and the third, and all of them in 3 dimensions are isolated from each other. So what we see here is that in open cell foam, the gas pockets, these are the gas pockets, this one, that form during manufacturing are connected to one another, creating an interconnected pathway. So in the case of an open cell foam, the gas pockets are connected to each other, whereas in a closed cell foam, we also have the gas pockets which are closed. These are closed or sealed off from the neighboring cells. They are sealed off from each other, and that is why we say that they are called as closed cell foams. Now this is how a foam will look like. So we have a sandwich panel here which has this as a skin, another skin, and this is how a core, a foam core looks like in the case of a sandwich panel here. Now when I talk about the non-homogeneous types of cores, so you can see that you can have corrugated cores. The simplest example of what a corrugated core can mean is in the case of a packaging material where you have a cardboard which is corrugated, so it has the same logic of the skins. There are cardboard skins there, and then the corrugations are there also of the almost the same material. But in a sandwich structure, the faces are, as we said, made of a stiffer material, and the core, which can be a corrugated core, but it can be of a different material, normally lighter material. Similarly, the core here can be in the form of a honeycomb also. We'll see what does it look like in our next slide. So we say this is how corrugated core can mean. This is basically a double corrugated core. So you have corrugations running in one direction in one core, and then you have the corrugations running in the second direction. So it's a double corrugation core. Now how does it honeycomb core look like, or honeycomb sandwich looks like? So you have this referred to as the honeycomb, which we say is a core material, and the face sheet, and maybe there are adhesive sheets through which the face sheet is connected to the honeycomb, and this is how it looks like. So you have the face sheet, the face, and the core. So this is traditionally what we say is referred to as a sandwich structure. Okay. This is how we have said that it is referred to as a sandwich structure. Now we have also seen earlier that we have been representing shaped materials as a different material itself, although we have known already that by shaping steel you do not create a new material, or by shaping aluminium with a shape factor of maybe 30-40 you do not create a new material, but it's a pseudo material which behaves which, because it has properties which does not match with those of the base aluminium with a shape factor of 1. That is why we say hypothetically it is a new material. On the same lines, we will try to analyze sandwich panels as materials, as different materials, or as equivalent materials here. So we'll say a sandwich panel can be understood as a material itself. So what we have seen earlier is that we have said that a sandwich is a structure which has faces and a core, and each of these, the core material as well as the face material, has its own density, its own modulus, and its own strength. But to take it as a material in its own, we can say that a sandwich here has got some equivalent properties. That means if I take a sandwich beam and then load it maybe in different conditions, you will observe a certain deflection, you will observe a certain behavior, and through that deflection, depending upon what load that you have loaded, you will be able to calculate its equivalent stiffness, its equivalent density can also be calculated, that what is the density of the sandwich material itself. So instead of taking it as a material composed of two materials, maybe a face and a core material, we can analyze it as behaving like a single material itself. So that's how we can compare it with our conventional monolithic materials. How do you do this? To do this, we calculate the equivalent material properties for the sandwich, and we then identify them like your composite material. So this is what we intend to do here. So this is what we have discussed already, that we can say that a sandwich is composed of two different materials in this particular case, a core made of material B and two faces made of material A. And we can then actually say that, okay, this whole of it can be equivalent to a material in its own. So we can say that this is the equivalent material having the same thickness D here, but I say now it is made up of a single material. So, but its properties are same as that obtained by a sandwich here. So you obtain certain properties like deflection, observation like deflection, which gives you some measurement of the modulus of the material. You can measure the density of this sandwich itself, and then I say that equivalent material will have the same density as obtained by making a sandwich structure of two type of materials B and A. So we define here equivalent material. We define here an equivalent homogeneous material which will have the equivalent properties as are obtained by making a sandwich out of material A and material B. And in this particular case, the equivalent material will have a density of rho bar. So this rho bar here is what? It is simply written as MA upon D. So what is MA? MA is the mass per unit area of this equivalent material, and D happens to be the thickness of this material. And what is E bar? E bar here is the equivalent modulus of this material, which is actually equivalent to whatever modulus that you obtained by subjecting this sandwich to a bending phenomena. And out of that we define that E bar is nothing but 12 EI upon BD cube. It is 12 EI upon BD cube. How is that possible? Because we are saying here that the equivalent flagellar rigidity E bar I bar is nothing but equal to EI. So E bar I bar is for equivalent material and EI is for the sandwich itself. So E bar I bar equal to EI. And what is I bar? For equivalent material, I bar is nothing but BD cube by 12. I can simply say that because I have assumed that instead of two materials, this is made up of a single material, single equivalent material, so that its I value or I bar value can be written as BD cube by 12. And this expression combined with E bar I bar gives me the value of E bar as 12 EI upon BD cube. Okay, so this what we are trying to say is that although a sandwich structure or a sandwich panel is not made up of a single material, it contains two materials combined together, and it actually goes well with our definition of the hybrid material. We have already defined hybrids as a combination of two or more materials which are combined together in a particular configuration and in a particular scale for a particular engineering application. And on that lines we say that this is a equivalent material which has the similar or which has the same properties as observed by making a sandwich of this particular dimensions of core B, core face A with thickness C, core thickness C, and face thickness T, and the total thickness is D here. Okay, so we have two we have two cases now running simultaneously in our analysis. One for the composite, one for the sandwich, which we say is made up of two materials. Core material is different, light material but less stiffness. Face material is what we say is a high stiffness material, and traditionally high stiffness materials will have high density also. Here is where your composite skins can be better than your metal skins, because composites, if you use a CFRP as material A, it will have high stiffness, but the density will not be as high as that of maybe titanium or aluminium or any other metal as such. And that is why we will find that in many applications where weight reduction is the criteria, CFRP panel, CFRP faces and a foam core or a honeycomb core are the most common types of sandwich which are used here. So we define here volume fraction of the face material on the same lines as we defined in the case of our what we refer to as a composite material. So we can actually say volume fraction of the face material, if I write it as F here can be simply written as 2T upon D, where T is the thickness of the face and D is the total thickness. So it is 2T because we are assuming it to be prismatic in this dimension. That is why we are only considering the area of cross section here. So F can be written as 2T upon D, which gives me the core fraction here as 1 minus F. That 1 minus f. It is 1 minus 2t upon d, which ultimately boils down to c upon d. So you have two terms writing. We are writing here f here, which is an important one for us to remember. We are writing f here as the volume fraction of the face material, and we are writing it as 2t upon d, and the core fraction we are writing it as 1 minus f, and this 1 minus f is then written as c upon d. Based upon this, we have already said that the density calculation can be simply done by using simple rule of mixtures, and it has helped us in finding out the density of the composite material also. And based upon that, I can simply say that rho bar will be the density of the sandwich here, which will be nothing but rho f into f, that is density of the face material into the volume fraction of the face material, plus rho c, density of the core material, into 1 minus f. And writing it in terms of the dimensions of the sandwich here, I can write here rho bar, that is the density of the sandwich panel that you are seeing here, is 2t upon d. We have just substituted the value of f here as 2t upon d into rho f plus rho c into 1 minus 2t upon d. So we will be making use of this expression. Please make a note of this expression for the density of the sandwich panel here, which is, as I said, similar to what we obtained for the density of the resulting composite, obtained by a simple rule of mixtures here. Now let's now start discussing this composite, the sandwich, as a beam. So if you look at this is a line diagram, and this is the cross-sectional views that you see. So the blue one here happens to be the core, and the orange ones are the two faces here. And if I treat it as a beam here, having a span length of L and having a mid-span loading at P, that is 3-point bending. The other dimensions which are here, C happens to be the thickness of the core. I forgot to mention here. This is B, the width of the beam, and D is the total depth of the sandwich, and T here, this T and this T is the face thickness here. So when I subject it to bending, let us say 3-point bending to be specific here, there will be deflection produced in this sandwich. This deflection will be because of two reasons. So if you go back to your basics on mechanics of solids, we have talked about the deflection produced normally by bending stresses, and we have said that the deflections produced by the shearing stresses are very, very small, and they have been neglected normally in your course on strength of materials. So that is why we have been only talking about the deflection obtained because of the bending stresses. But here we cannot do that. We'll see. I'll tell you the reason why it is not such. Why we cannot neglect the deflection because of the shearing. Because the basic reason happens to be because the core here happens to be very weak, because we say it's not a very stiff material, it's a very less stiffness material as compared to the face of the material. So I'll come back to it in a moment. So to understand that, we say the total deflection here is because of two types, because of two reasons: because of bending, the deflection contribution by the bending, and the deflection contribution of the shearing here. As I said, in a homogeneous beam, because if it was made of steel or aluminium only, the deflection because of the shear stresses is normally neglected. But in a sandwich beam, which are mostly subjected to normal stresses, the core of the sandwich is subjected to the shear stresses. So that is what we see here, that if you recall the distribution of the normal stresses of cross section here, the distribution of the normal stresses in bending tells me that the maximum normal stresses will be near to the face, and at the neutral axis the normal stresses are 0, and the material of the core is subjected to less normal stresses as compared to the normal stresses of subjected to which the face material is subjected. But when I talk about the distribution of the shear stress, so this was the distribution of the normal stress, but when you talk about the distribution of the shear stress in the beam, This is what we recall. If you recall only just for a homogeneous I-beam itself, we understand that the shear stress distribution, you have the maximum shear stress happening in the core in this region, whereas the maximum normal stress was happening in the outside region. So the core here, the blue portion here, is subjected to shearing, and the shearing stresses are higher in the core than that are available to us in the face of the sandwich, and that is why we cannot neglect the deflection produced by this shearing also, which normally is there for which is there for the core material here. So that's the basic reason why we say that we cannot neglect the deflection produced because of the shearing here. That's the basic reason happens to be because the modulus of the core material is very small as compared to the face material. The shear deflection in the core cannot be neglected. So that's what I already said, that the core material is very weak material as compared to the face material here. So let's move forward with this analysis here. So I continue with the same analysis of a 3-point bending in a beam, and we said the total deflection here happens to be delta, and it is composed of two portions, delta B and delta S. Delta B is because of the bending stresses, and delta S is the because of shearing. And what is delta B? Delta B here, delta B is traditionally found as PL cube upon C1 EI. This is the formula that we normally use for finding out deflection because of bending stresses. It is PL cube upon C1 EI. C1 is a constant. For a 3-point bending, this C1 value goes to 48. So it is the PL cube upon 48 EI. Now I am writing EI equivalent. Why do I write EI equivalent? Because if I write PL cube upon C1 EI, that is for a homogeneous beam. But because this is not a homogeneous beam, this is a sandwich beam which has two materials. A core is different and the skin is different, and that is why the flexural rigidity part, that is EI, which is referred to as the flexural rigidity or the bending stiffness of the beam, is also to be taken into consideration for what we call as a sandwich beam, not as a single monolithic beam, and that is why we write that it is PL cube upon C1 EI. In our next steps, we will try to find out what is the value of EI equivalent, that is what is the equivalent bending stiffness, and then we will see that how does it helps us in further analyzing this topic here. So when I talk about EI equivalent, what is that? EI equivalent happens to be the equivalent flexural rigidity of the sandwich panel here, or a sandwich beam here, and it is composed of these three terms. So what are these three terms? The three terms, if you look at them carefully, the first term is about the flexural rigidity of the core material. It says it is what? It is EC into IC. So what is EC? EC is the modulus of the core material, and IC is the moment of inertia of the core material only, which is what? It is BC cube by 12. So this is how it is here. This is BC cube by 12. So the first term here refers to the bending stiffness value for only the core material. It is EC into BC cube by 12. Now then plus 2 times. So I am writing 2 here because now I am coming to the phase. So there are 2 phases, and that is why I am writing 2F. So it is 2 times. Forget about 2 times for the time being. What I am writing here is EF, that is the modulus of the face material, and IF, which is BT cube by 12. So we say BT cube by 12 here, but this BT cube by 12 is the moment of inertia of the face material, this orange material, about its own centroidal axis, about this centroidal axis, not about the centroidal axis of the sandwich panel itself. And that is why the next term helps us. What is the next term? The next term here is nothing but coming out of your parallel axis theorem, so that you are able to find out the the I value and the EI value around the centroidal axis of the beam here. So the first term was for the core, that is what we say, the first term is for the core, and the next two terms are for the face. So this is what it is, EF into BT cube by 12 plus, what is this? It is A into D square, area, into the square of the distance between the two axes, that is the central axis of the face and the centroidal axis of the beam, which is here C plus T by 2 square, that is D square, into B into T. B into T happens to be the area of the face. So this EI equivalent can be written as these three terms, the first term representing the bending stiffness of the core, and the next two terms representing the bending stiffness of the face material here. Now so this is how what we say is the equivalent bending stiffness here. Now going forward, I carry out with this example, this only, and what I have is, this is an expression that I get for the equivalent bending stiffness for your sandwich panel here. There's another way I can simply try to simplify that to some extent here, so that you take out these 2's from here, and we need to know in this expression here that the EF values are much higher than EC values. That is, modulus of the face is very high as compared to the modulus of the core, and the core thickness C is also very high as compared to the face thickness T. So these two things we need to put in mind here. So we have found the equivalent bending stiffness, EI equivalent, in terms of this expression, which I write here. And there's another way to write that. So what we have done is that we have taken the core separately, and then the stiffness of the face around its own centroid, and then the stiffness of the face around the centroid of the neutral axis. But there's another way to do that in a different way, by which you will get this expression. So these two expressions, this one and this one, they are equivalent, but they look different to some extent. What is the difference here? The first term happens to be the same. This is the same term that you observe here for the core. So the first term for the core stiffness happens to be the same in these two expressions here. The second term that you find here, that instead of writing in terms of parallel axis theorem, what I have done is that I have simply written it as the difference of the moment of inertia between the total overall rectangle minus the area of this blue rectangle, and that is how it comes to B by 12 D cube minus C cube into EF. So either I use this expression or the second expression, they are same, they are equivalent, they are same. Both of them give me the EI value, that is the equivalent bending stiffness value for this beam, when it is subjected to bending here. Now taking forward with this, so I say that we have already written that delta B was written as PL cube upon C1 EI equivalent, and I have already found lately the value of this term. EI equivalent has been found as this expression, that is the core portion here, and this one is for the face portion here. And the next step will be that I will then simply substitute this EI equivalent in this expression for delta B, and this gives me delta B as 12 PL cube on C1B D cube minus C cube into EF plus C3 plus C cube into EC. So this is as far as the delta B is concerned. Keep it in mind that the total deflection was sum of delta B plus delta S, and we have written only for delta B for the time being. Then I will go through now what is the shear stiffness, the delta S part. So the delta S part, for that purpose I need to first find out AG. AG here is equivalent to EI. So EI is bending stiffness, AG is shear stiffness, and AG is written as BD square upon C into GC. Where what is GC? GC happens to be the shear modulus of the core material here, which then gives me the value of delta S, that is the deflection because of the shearing term here, as PLC upon C2. C2 is another constant, so C1 is a constant for your bending stiffness, C2 is a constant for your shear stiffness. We will see in the next table how these two constants vary depending upon the type of the beam. D square into B into GC. So this tells me that what is the value for delta S. And going forward now, what I have done, the total deflection then delta will be sum of delta B plus delta S. So I have combined delta B and delta S here. So I have two constants C1 and C2, and the C1 and C2 can be taken out from these tables for our 3-point bending. For our 3-point bending, C1 was 48 and C2 is 4. So C1 is 48 and C2 is 4. If that is a different type of bending setup, you can then see that the values of C1 and C2 can be found from there. Okay, so what I have done, we have found that how you can find out the deflection delta in terms of the various constituents of the sandwich panel here, in terms of its dimensions, that is D, C, and in terms of its material properties, that is the face property and the core property, and obviously there are certain constants here. Similarly, if you recall, we could have taken the sandwich panel as a equivalent homogeneous material only, without considering EF and EC and C and B and D. We can say that it is a single material, and still it will give me some deflection where I can very easily find out the deflection of that in an experiment here. So in that particular case also, I can find out the value of delta here. Now this delta is actually in terms of the properties of the sandwich panel, whereas this delta is what you find experimentally without looking into what is into the sandwich. I say it is a single equivalent material. So it will be what? It will be nothing but PL cube upon C1 E bar I bar. PL cube upon C1 E bar I bar. So E bar and I bar I have substituted. I bar is substituted here as the equivalent I value of the equivalent section. It is nothing but BD cube by 12. So we are not concerned here about the C value, that is the core thickness, and the T value. We are not concerned about that. We are considering the total sandwich as a single material, and that is why I am writing its I bar value, equivalent value of I, as BD cube by 12. And that's what we see here, that we already said that the equivalent density rho bar can be MA upon D, and E bar value is nothing but now we have E bar value also, which is what 12 EI upon BD cube. Okay. So what can be done now? Okay. So I have this value of delta and this value of delta. Obviously they shall be equal. What I observe here in taking the sandwich as a single material, as a equivalent material, delta, this delta can be equated to this delta. That is, we are predicting if we are taking them as two different materials in terms of EF and EC. So this delta and this delta can be then equated, and when I equate these two terms, this is what I get. When I equate these two terms, this is what I get. We will try to solve it in one of the assignments here. It's quite easy to do, and I'll send you the assignment later. And this is what I get. I get 1 upon E bar. It's written here E bar flex, but it is the same 1 upon E bar. So this is 1 upon, sorry, this is the E bar. This is the E bar value here. So delta, we say delta is now 12 PL cube upon C1 E bar BD cube. We equate this term, the blue one, to this term, 12 PL cube on this. And when I do that, I can then get this expression here as that E bar was there. So 1 upon E bar. This expression will help me to find out E bar actually. That is what we are saying. The equivalent flexural stiffness can be predicted for a composite, for a sandwich. And 1 upon E bar is then written as 1 upon EF into 1 minus F cube plus EC upon EF 1 minus F cube plus B1 upon B2. So this B1 upon B2 is actually nothing but it shall be replaced by C1 upon C2 in our case. I'm taking it from the textbook. So this is C1 upon C2 actually. This is C1 and this is C2. But the book takes it as B1 upon B2. So but this B1 upon B2 is nothing but B1 is equal to C1 and B2 is equal to C2. And then it's D upon L square and 1 minus F upon GC. And this is a very useful expression. So this expression helps me to predict the E value, equivalent flexural modulus value. Keep it in mind, it is different from the flexural rigidity. It's not a E bar I bar term. It is only E bar. That is, what will be the equivalent flexural modulus of the sandwich structure, and how it will be different from the E value of the face, that is EF, and E value of the core EC. And we have written it in terms of the properties of the core and the face, that is EC and EF, and the geometrical geometrical portion, which is in terms of F, the volume fraction of the face material, C1 and C2. This, as I already said, B1 is equal to C1, B2 is equal to C1, that is the loading conditions. D upon L, again a geometrical condition, and GC, again a mechanical property of the core material. And when I do that, we shall be able to plot something like this. I'll show you exactly how we can do this exercise, and then we can plot it to see that. So what it tells me, so if you look at this chart, let me go to, I'll just briefly explain, then go to the next slide. What we have done is that we are plotting the flexural modulus E, this E or E bar to be specific here, and density is nothing but a modulus versus density chart. And what you observe here is that we have the red dot here representing the face material, and this green dot representing here the core material. So you have the face material, means the face here is of a composite made of CFRP, that is carbon quasi-isotropic weave, and foam is used as a core material for this beam, for this sandwich. And we'll be plotting this curve here for different values of F, for different values of the volume fraction of the of the face material. So it is F equal to 2T upon D. So these dots are actually telling us we are plotting the E bar value and the density value. So keep it in mind that you have predicted the density also using the simple rule of mixture. So you can use this density, that expression, and this E expression for finding out, for plotting these values for B1 upon B2 as 3. This one is plotted for B1 upon B2 or C1 upon C2 as 3, and D upon L as 0.05. So you can keep on doing this for different values of B1 upon B2, that is for different loading conditions, and different D upon L ratios. D upon L is what? D upon L happens to be basically the ratio between the depth of the beam and the length of the beam. Traditionally, shear stresses are more important for short length beams, and that is why this D upon L is a term which is coming into our discussion here. I'll take you to the output of now. If you